Hello and welcome back to Technology Now, a weekly show from Hewlett Packard Enterprise where we take what's happening in the world and explore how it's changing the way organizations are using technology. We're your hosts, Michael Bird
and Aubrey Lovell. And in this episode, we are looking at improving the energy efficiency and sustainability of our computer workloads by shifting them around the world in real time, something called geo-distribution. Energy needs for IT and data centers are rising, especially as AI grows in popularity. The International Energy Agency says that the global demand for electricity consumption just to run our data centers could double by 2026. And there's a link to that in our show notes. And it's not just electricity. There's also a growing demand for physical hardware to populate our data centers and water to keep these systems cool.
So the idea of distributing workloads around the world to be run wherever electricity is cheap, water is plentiful, and resources are in lower demand sounds simple. But how feasible is it to move workloads around the world? How much energy could it actually save us? And why does it matter? Well, if you're the kind of person who needs to know why what's going on in the world matters to your organization, then this podcast is for you. And if you haven't yet done so, do make sure you subscribe on your podcast app of choice so you don't miss out. Right, Aubrey, let's get into it.
Let's do it. So, as we said a moment ago, the energy demands of our data centers are rising. And according to an IEA report, in 2022, data centers consumed over 430 terawatt hours of electricity. However, they estimate that by 2026, that could potentially double to more than 1,000 terawatt hours. So that's a pretty significant increase. This generates a lot of heat, which also increases the need for the effective cooling of these data centers. Now, according to research by ING, which we've linked to in the show notes, the average US data center uses as much water every day as 100,000 homes for cooling, air conditioning, and humidifying. With a quarter of the world's data centers in the US alone, and many of those in areas where water is in short supply, water is an increasingly important consideration.
Geo-distributing workloads is one potential future solution to address the issue. It involves looking at real-time global energy production, ideally from renewable sources, and a load of other factors, including weather, water tables, and more. By comparing these factors, as well as compute availability and the lag between data source and data center, you can find the most sustainable locations to perform a task. Ideally, shifting the workload so quickly that the user doesn't even know it's happening. Clearly, that's going to be a lot more complicated than it sounds. So here to walk us through what it might look like is Cullen Bash, the Vice President of Research and Development at HPE, who is leading the Systems Architecture Lab at Hewlett Packard Labs. Thank you so much for joining us, Cullen. So, in layman's terms, can you tell us what a geo-distributed workload actually is?
Our research is about reducing the environmental impact of data centers by moving workloads that run in data centers to regions where their environmental impact is lower. And this was motivated by the need to reduce global carbon emissions to net zero by 2050, which came out of the 2015 Paris Agreement. And it's aligned with Hewlett Packard Enterprise's target to reach that goal of net zero carbon emissions by 2040. This is active research with our collaborators at Colorado State University. And so we haven't reduced this to practice. It's very much in the research stages right now. So I would say that research is always one of those things where you never know exactly how long it's going to take to finish something and be able to commercialize it, but we're at least a few years away.
So we know there are 3 ingredients to this puzzle, right? What are they and how are they balanced?
Data center environmental impact is primarily linked to carbon emissions, and it's linked to carbon emissions through energy consumption indirectly, right? As energy is generated by different sources, carbon is emitted in different rates, and so as energy is consumed, we're indirectly emitting carbon. The second variable is water consumption, and this comes indirect and direct. Data centers indirectly consume water because water is consumed when energy is generated. So that's sort of an indirect, like carbon, it's indirect. But data centers also consume water directly to remove the heat that is generated within the data center. And so we'd like to minimize both carbon emissions and water consumption But if we only look at sustainability, just those two variables, without considering cost, then the eventual uptake of any solution we come up with is going to be minimal. We have to consider cost. Cost of energy can be as variable as carbon, as water. So that's why all these are tied together. If we think about any individual region, the cost of energy in that region is a function of how that energy is generated. It's a function of the resources that go into generating that energy, water, other things like that. So all of these three things interplay in a way that's very interesting.
So what does the algorithm actually do?
So the algorithm that we're using is part of a broader class of algorithms that are under the umbrella of multi-objective optimization. And so what we're doing is co-optimizing energy cost, carbon footprint, and water usage simultaneously. What's interesting about this is that this sort of multi-objective optimization problem is very complex. It doesn't have one single answer. For any given individual solution, we can't improve one variable, like carbon emissions, without making another variable worse, like water consumption or cost. Think about an elastic, two-dimensional surface that's stretched out. So in my mind, I think about a bed sheet. I don't know why I think about a bed sheet, but I do, with four corners all stretched. So the bed sheet's really flat and taut. That represents our solution space. Somewhere on that two-dimensional space is our set of solutions that we're trying to find. And then take a rectangular object. So think, I don't know, a piece of rectangular wood, something that's kind of heavy, place it somewhere in the bed sheet, and you'll get a depression. That depression represents our solution space. That's what we're trying to find. Now, the bed sheet could have a baseball on it. It could have a tennis ball. It could have a golf ball scattered around, also creating depressions. Those are sort of point solutions that represent local optimums for our solution, but not the global optimum, not that set that we want to try to find. So we want to try to ignore those, right? And try to find that global optimum. Now we start anywhere in the solution space, right? Pick a point and then make a guess at where we should move within this two-dimensional surface to find our set of solutions. And regardless of the outcome, what we do is use machine learning to learn over time to make better decisions faster until we finally get to that optimal set. And the result is that we get more accurate solutions at a faster rate than previous algorithms. And so when we need to make those workload placement decisions, we can do so quickly, we can do so accurately.
So, how feasible is it to actually move those workloads around the world? How much more energy resource efficient could that make them? And can every workload be distributed?
It's certainly feasible within a geopolitical region like the United States or the EU. Once we cross geopolitical boundaries, it could become more challenging, might even become impossible, depending on where that region might be. So it really depends on where an enterprise has its operations, depends on the local rules governing operations in that area. With respect to efficiency, it's an interesting question because the way I view where we are right now, we're in a bridge period in time. We're bridging the gap in time between when there was 100% non-renewable energy feeding the grid, the electricity grid, and 100%, or as close as we can get to it, renewable energy feeding the grid, right? We're not at either of those extremes. We're somewhere in the middle trying to get as far to renewable energy as we possibly can. So during this period, the grid varies in carbon intensity by space, so think geographic region, and by time, by seasonality, by time of day. The more it varies, the more we see this variation, the more techniques like the one we're discussing today can exploit that variance and reduce carbon. So think about it like this. Think about the follow the sun concept. That's how I often think about it. In the daytime, there may be an abundance of solar energy powering the grid, for example. During the night, that drops to zero in the same region. So the concept is to follow the sun with the workload. And that's simplistic because the grid is fed by numerous renewable sources that change throughout the day. Solar and wind are the ones that we think about most, but there are others as well. The concept, though, is the same. Move the workload to where and when there is more renewable energy. Can every workload be distributed? It depends on the workload. So the short answer is no, not every workload can be distributed. The longer answer is that workloads that are dependent on data in particular are difficult to move because data is often difficult to move. If we move the data, it takes time. That creates a performance impact. And so those types of workloads are often off the table. There are also sensitive workloads, that need to be housed in a specific area. We can't often move those. but some workloads are less dependent. A good example of both actually are in AI models. Think large language models, something like that. These models take a long time to train. They take a lot of data to train. And so they often have to stay in one place. They can't move around. But once they're trained, those models can be deployed anywhere and then can be invoked when needed. So those are great candidates for this type of work.
And what are the potential trade-offs and benefits for future users?
Performance comes into play a lot. So if we want to try to reduce energy consumption, oftentimes it's at the expense of performance. If we want performance, we think about a computer system. We want to turn that system up to maximum. And when we do that, we get a fast system. We also consume more energy, almost always. And there are techniques that we're looking at to trade that off in a way that limits the impact of performance. But in this case, if we think about workload moving farther from the end user, right? If I'm in, let's say, the West Coast of the United States and it's dark and I want to take advantage of sunlight, somewhere else, then I may have to go on the other side of the world to do this. Well, there's latency associated with that. There's the time it takes to make that request and then to get that response back. And this may not be a big deal for some users and for some workloads. For others, it may be. So there's this performance versus sustainability trade-off that we have to make. Ultimately, we think it's going to be important to expose these trade-offs to the end user so they can make an informed decision. They can understand that, all right, if I do take a hit on performance of X amount, but there's an environmental benefit for that, maybe that's a trade-off that they're willing to make, maybe not, but that ultimately should be in the hands of the end user.
All right, thanks so much. There are some amazing insights in there.
So now it is time for Today I Learned, the part of the show where we take a look at something happening in the world that we think you should know about. Aubrey.
All right, I'm doing my stretches, Michael, because this is a long one. All right, so it's one for me this week. A team of scientists in China have created a brain for a robot developed from human stem cells, giving the robot the ability to avoid obstacles and grip objects. I can't tell if I'm excited about this or if I'm actually terrified. How do you feel?
Yeah, a bit of a mixture of both.
Okay. Well, they have developed a system that brings together matter from the human brain with a neural chip that translates the neuron signals into code, which can power the robot. So brain cell-based chips aren't entirely new. They've been used for basic robotic tasks in the lab, such as unguided movement before. However, this is a massive leap in the technology. The complexity of the new system required the scientists to consider a whole raft of challenges, including how the biological elements of the chip were fed with nutrients, while also trying to train the chip to perform more complex operations by, in the loosest terms, showing basic intelligence. Sounds like a movie. The project is still in the early stages, and this isn't a brain in a jar so much as a collection of cells on a chip, but the researchers hope to one day have a robot that is a fully intelligent hybrid computer, able to bring together the best of machine learning and biological neural network forming and problem solving. Creepy or cool? Well, that's up for you to decide, dear listener.
Yes, Aubrey, that really is mind-blowing.
Very good.
There we go.
Well
there we
done.
go. That was there on a platter, wasn't it? Anyway, thank you so much for that, Aubrey.
All right. So now it's time to return to our guest, Cullen Bash, to talk about some of the challenges and potential benefits of geo-distributing our workloads.
So, Cullen, how close is this to being something that could actually be implemented in practice?
The next steps, I think, are to expand the study to a wider variety of workloads, really try to understand which workloads are best suited for this sort of technique, which are not. Can we make modifications to how we think about workloads and their execution to make them more compatible with this technique, or vice versa? Are there adjustments we can make to accommodate a wider variety of workloads? We need to investigate the impact on performance. That's a big one that we just described, and how to expose that to the end user so they can make informed decisions. And ultimately, we need to start reducing this to practice. It's a paper study right now. That's where we've taken it. We've developed these algorithms. We've simulated the environments. Now we need to actually start testing this in a real environment.
In parallel to this, you're also working on something similar on a more local level with data centers themselves, right?
We're working on building what we call digital twins. A digital twin is a digital representation, a virtual representation of a physical system. It can be anything. You could build a digital twin of a car, an airplane, a house, a building, it doesn't really matter. What matters is that the physical system has a connection back to that virtual system. It sends data on the state of the physical system back to the virtual system so that virtual system stays up to date and evolves over time as that physical system changes with time. And so we're building digital twins of data centers. And we're using these to perform similar optimizations at the local level that we just talked about at the global level. So we're essentially looking at local grid carbon intensity, where that data center is located. We're looking at energy costs, where that data center is located. We're looking at the workload that data center is having to execute. And then we're optimizing that. And we're using artificial intelligence and reinforcement learning, in this case, another class of artificial intelligence, to do that optimization. So we tend to talk a lot about the impact that AI is having on energy use, on the explosion of the needs for energy to feed these AI models, both in training and in inference. But these are good examples of how we're using AI to improve the sustainability of systems.
So, Cullen, why is this research important? Like, why should our audience be paying attention?
We need to be looking at a suite of technologies to improve the sustainability and energy efficiency of IT in general and data centers in particular. There's never going to be one solution to solve this problem. There, by necessity, has to be many different solutions. An important aspect of geo-distributed workloads and what we're talking about today is that they have the potential to reduce environmental impact, but also reduce cost. And when we can identify technologies that have the potential to do both, then they warrant attention and they warrant further exploration.
Cullen, thank you so much. It's been really, really great to talk. And listeners, you can find more information on the topics discussed in today's episode in the show notes.
All right. Well, we're getting towards the end of the show, which means it's time for This Week in History, a look at monumental events in the world of business and technology, which has changed our lives. And Michael, what do you have for us today?
Well, the clue last week was, since 2014, this day is sure to put a smile on your face. And it was, of course, World Emoji Day. Yes, hard-hitting this one, Aubrey. Celebrated on July the 17th every year because that's the date commonly shown on the calendar emoji. Clever, obviously. The day doesn't really have any purpose other than gratuitous emoji use and, of course, to announce new suites of emoji and emoji-based products. So there is that. So not the most serious one this week, but actually probably the one that most of us can relate to day. Aubrey, what's next week's clue?
So next week's clue is it's 1963. Stay right there. Know what it is? Well, I don't, but if you do, keep it to yourself. And that brings us to the end of Technology Now for this week. Thank you again to our guest, Cullen Bash, Vice President of Research and Development at HPE. And to you, our listeners, thanks again so much for joining us.
Technology Now is hosted by Aubrey Lovell and myself, Michael Bird. And this episode was produced by Sam Dattapaulin with production support from Harry Morton, Zoe Anderson, Alicia Kempson, Alison Paisley, Alyssa Mitri, Camilla Patel, and Chloe Sewell.
Our social editorial team is Rebecca Wissinger, Judy Ann Goldman, Katie Guarino, and our social media designers are Alejandra Garcia, Carlos Alberto Suarez, and Ambar Maldonado. Technology Now is a Lower Street production for Hewlett Packard Enterprise.
And we'll see you at the same time, the same place next week. Cheers!